We're going to continue our discussion of approximating area in the plane. This is going to be much like the last videos were. We're still going to be using rectangles to approximate the area, but I am going to give you some terminology that I want you to make sure that you know, because this terminology is used on the AP. There was a gentleman named Riemann. He did a lot of work in the XY coordinate plane. He was a brilliant man, died early of a disease, but these sums where we're using left endpoints, right endpoints, and midpoints are actually called Riemann sums. He was the one that came up with the idea that we could approximate the area by adding up different areas, how many ever we wanted to add up, in the plane using areas of rectangles, a geometric formula that we all know by heart. And he said we could do it using left endpoints, and you can see here's the area in the plane where the upper left corner of each rectangle is intersecting our curve. And I also want you to notice we can have area rectangles, finding area, below the x-axis. The examples that I did in the last set of videos were all above the x-axis, but there's nothing saying that it has to be above the x-axis. We can find the entire area trapped in between a curve and its horizontal axis, even if the curve goes below the horizontal axis. So additionally, we had midpoints. Here you can see that this is the heights of these rectangles come from the midpoints of the intervals that are the widths along the x-axis. So Riemann stated that area under a curve could be determined by a sum of areas bounded by the x-axis. He stated that area above the x-axis, and this is important, would be positive area. So anything up here would be positive area. Those two pieces, area 2 and area 3, he would consider positive area. And any area below the x-axis would be considered as negative area. So this would be negative area, and this would be negative area. Area 1 and area 4. And as far as Riemann was concerned, he called this the accumulated area. So the total area, or the area in the plane, would be taking the positive areas and subtracting from those any negative areas that might be found. So this would be the accumulated area in the plane. And again, that could be approximated by areas of rectangles. How many rectangles? They'll tell us how many rectangles to use. It's never left to our imagination. Riemann also used the idea of an infinite number of rectangles in order to find the area, and he placed his rectangles not at the endpoints, but at any convenient point that he could find. So here is an example, and I said this in the last set of videos, that we don't always have to have the same width. These rectangles don't have standard widths. There's width 1, here's width 2, and here's width 3. All right, here they've called it the change in x1, the change in x2, and the change in x3. We don't have a function rule that will tell us what our heights are, but we do have the graph of the function, and we can approximate here what the heights of these rectangles are by looking at where they would intersect the y-axis. So our areas are still going to be width times height. The only difference here is the widths are not all the same, so we're going to need area 1, and we're going to need area 2, and we're going to need area 3. And as we learned on the last slide, this is negative area. This is negative, this will be positive area, and this will be positive area. Why? Because the output of my function here is a positive value. The output of my function here is a positive value. But the output of my function here is a negative value. So I don't have to do anything fancy to get positive area versus negative area, and that's accumulated area. So area 1, we have a width we can see along the x-axis. We start at x equal 1 and we stop at x equal 2.5. So that width of that first rectangle is 1.5. And the height of that rectangle appears to be about 4. And now area 2 The width of area 2, we start at 2.5 and we stop at 3.5, so that width is 1. And the height of that rectangle appears to be 3. And for the third rectangle, that width appears to be, we go from 3.5 to 5, so that width is 1.5. And now the height appears to be about negative 2.5. And again, that's where this y value right here at negative 2.5 is where the negative comes into play. So the total area is approximated by those three areas added together. 1.5 times 4 plus 1 times 3 plus 1.5 times negative 2.5. So there's a Riemann sum without standard widths. Most of the time we're going to be given a function, we're going to be told what endpoints to use, we're going to be told or shown what interval, here's negative 2, here's negative 2.5. We're going to be told over what interval that we are going to be approximating the area. Remember, area below the x-axis will be negative, area above will be positive. So using right endpoints on the function y equals 2x, let's approximate this area. Now our widths are going to be standard. We can see that from 0 to 1 we have 4 rectangles. So each of those widths are 1/4. All right, and we can see that the same is true here. This width is 1/4 and 1/4 and 1/4. So all of our widths are the same, so let's just factor that out front, and then we just need to worry about the sum of our heights. Now, we're going to use right endpoints. So for this rectangle, I'm going to use this point. I want to know what the height of my function is when I put this x value into it. And my function is 2 times whatever x value I put into it. So here's negative 1/4, negative 1/2, negative 3/4. I said that was negative 2. It's negative 1. That's negative 1/2. So negative 4/4, that's negative 5/4. So when I put negative 5/4 into my function, I'm going to get negative area, right? It's 2 times whatever I feed it. The next one is going to be 2 times negative 1. And then 2 times negative 3/4. Those are all my right endpoints. And then 2 times negative 1/2 and 2 times negative 1/4. And then the height of this one, since it's a right endpoint, is going to be 2 times 0 plus 2 times this height, which comes at 1/4, positive area, plus 2 times 1/2 plus 2 times 3/4, and I'm using right endpoints, so I do have to use that last and final right endpoint right here. So all of my heights are coming from the right endpoints of the interval that I am finding the area for. So in that case, I don't use the height at the leftmost endpoint. So we've seen that before. Let's work a few more examples here, and I think we can get through this in one video. So here's our function, y equals x squared plus 2. They want us to use left endpoints, and we have 1, 2, 3, 4, 5, 6 rectangles, and we are on the x-axis at 1, 2, 3. So the left endpoint is 0, the right endpoint is 3. So our widths are 3 minus 0 divided by the number of rectangles. All of our widths are 1/2. So I can factor that out front and just find the sum of our heights. We're using left endpoints. So there's 1, there's 1, there's 1, there's 1, and there's my final one comes from right here. So this is 1/2, 1, 3/2, 2, 5/2, and 3. So my heights are coming from plugging my x value into my function. There's my first height using left endpoints. My second height is 1/2 squared plus 2. My third height, right here, comes from 1 squared plus 2. My fourth height would come from 3/2 squared plus 2. And then 2 squared plus 2. And finally, 5/2 squared plus 2. That would be my final height. So there's the approximation for that area trapped under the curve y equals x squared plus 2 from x equals 0 to x equals 3 and above the x-axis. We could do the same thing with right endpoints. Our widths are going to be the same. All of our widths are 1/2. That hasn't changed. Our area now is approximated by our widths times the sum of our heights, but now our heights are coming from the right endpoints, right? So our first one is 1/2 squared plus 2. The second one is 1 squared plus 2. The third height is 3/2 squared plus 2. The fourth height is 2 squared plus 2. The fifth height is 5/2 squared plus 2. And the last and final height is that right endpoint at 3 squared plus 2. So let's do this final example. Same function, same interval, same everything. Our widths again are 1/2. Our area is approximated by 1/2 times the sum of the heights. But now all of our heights come from these midpoint values. The midpoints are what we're going to plug into our function. So let's find those midpoint values. So this is 1/4, there's 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, 9/4, 10/4, and 11/4. And of course that would be 12/4, which would be 3. So now my heights are 1/4 squared plus 2. That's the first height. 3/4 squared plus 2. There's the second height. The third height is 5/4 squared plus 2. Fourth height is 7/4 squared plus 2. 9/4 squared plus 2. And finally, the last midpoint, 11/4 squared plus 2. So hopefully between last lesson and this lesson you get a really good idea of how we can use a finite number of rectangles to approximate the area trapped in the plane, either above or below the x-axis, in between a function and the horizontal axis. And we can do it in 3 distinct ways. We can do it by finding our heights of our finite number of rectangles using the left endpoints, the right endpoints, or the midpoints. So hopefully you can come tomorrow. We'll do some Riemann sums, and again, that's terminology that you need to know because you'll be given a function and you'll be asked to use a Riemann sum with a finite number of rectangles. You'll be told whether to use a left endpoint Riemann sum, a right endpoint Riemann sum, or a midpoint Riemann sum. So make sure you can do this and make sure you practice it a lot. Come next time ready to do some homework.